The first nail in the coffin of using monomials as a modal basis has to do with the linear independence, or lack thereof in the monomial case, of our basis. So if we normalize our basis with respect to the L2 norm, so in other words, if we have some particular function g, the L2 norm of it is the square root of the inner product of the function with itself, and we apply this to a particular monomial basis x to the I, we get a normalized version that takes on the following form. So this is essentially the normalization factor associated with this particular arbitrary monomial. So consider the inner product of two adjacent basis functions. So here's one normalized and here's the other normalized monomial bases, and they're only differing by 1 in terms of their order. And we can take the expression we developed here and get the product and then integrate this, and then we get this expression for the inner product. So recall that we just said that the inner product of two functions, if they're orthogonal, should be 0. And recall from linear algebra that linearly independent vectors are specifically orthogonal. So that is, their inner product is 0. But take a look at our monomials for, let's say, a comparatively moderate value for the order of our monomial. So we can imagine maybe, let's say it's like a 7th order or something like that. If we put a 7 in here, 7 squared is 49. 49 times 4 is approximately 200. So this is 1 minus 1 200th. And then we're taking on top of this, so that's very nearly 1. And then on top of that, we're taking the square root of that. So that's even closer to very nearly 1. So that indicates that these two bases are really poor in terms of being linearly independent. So if you were to look at, a low order, so if you put 1 in here, okay, well, that's a quarter, so this is 3/4, and square root of 3/4. So it's not quite as bad, but even at moderate values for the moderate order monomials, you're going to have problems where the inner product is close to 1, and so therefore you're very nearly linearly dependent. So why do we care whether they're linearly independent or not? Well, if two basis vectors are very nearly dependent, then they look almost identical to each other in terms of their effect on the overall recovery of our solution approximation. So that means even small perturbations can lead to trouble finding the correct solution. So imagine if you had some approximation to your conserved quantity, and it was equal to some coefficient times some basis 1 plus some coefficient times some basis 2. If basis 1 and basis 2 look very similar to each other, you could easily change the coefficients a1 and a2 by quite a bit, and it wouldn't ultimately impact the solution approximation that very much. Because this looks very much like this, we could substitute them almost for each other if they're very nearly dependent. So that means if we're working backwards and we have a solution approximation that we'd like to get by determining our coefficients, it can be really difficult to see what value for these coefficients would need to be that gives us our desired point. And if we were to then change our desired approximation by even a little bit, that could mean that these coefficients change by a drastic amount, which has serious consequences for our solver. So the other set of problems associated with the monomial basis has to do with what's called the Hilbert matrix. So one alternate way to consider this is look at the mass matrix for this monomial basis. So let's say we didn't realize that our bases are very nearly dependent, and we moved forward and started trying to use this in our discrete solver. Well, if we think about it, okay, so here's a recall from our simple solver that our mass matrix is the integral of our solution approximation times our weighting bases. Our solution approximation bases times our weighting bases. And let's say that, they're two different ones. if we chose our bases to be monomials, then we can see that if we look at, let's say, where we have a fourth order method for our approximation space, then we could see that our mass matrix in that case is going to be 5x5, including the constant. So 4 non-zero order terms and then a constant term. So we could see then that this is going to be, let's say I goes across like we did in the linear. So we have 1x squared. And I'm not going to write the whole thing out here, but then you can imagine, okay, well, so here's my weighting basis, and this does something similar, right? So in this particular case, so we'll write it alongside of here to make it clear what's happening. So we're essentially distributing this through, right? So if you're multiplying it by 1, we get 1x squared. The next one, we're multiplying this by x, so we get x squared, x cubed, x fourth. And it's pretty easy to see a pattern here, right? That the equal order terms all occur along the diagonal of this mass matrix. It turns out that if you look at this, and we're actually looking at the integral of this, right? So again, we'll abuse notation and say we're integrating our mass matrix here. And let's say we're integrating from 0 to 1. Well, what does this end up looking like? Okay, so let's more neatly represent our matrix over here. So again, we'll only look at the first couple of values to see what the pattern is, but we have the integral from 0 to 1 of our matrix. So we have additional terms in here, x squared, x cubed. So they increase both in the I and j direction. And if we look at what this evaluates to, well, it's pretty obvious to see that any particular term is going to look something like, let's say the x squared term is going to look something like x cubed over 3. But we're evaluating that from 0 to 1. So at 0, this term is 0. And at 1, the x cubed is 1. And indeed, for any of these terms, it'll be 1. So that all we're left with is 1 over the 1 plus the value of the exponent. So this gives us then the following matrix. Etc. So why is this an issue? Well, it turns out that this is a Hilbert matrix, so which is a well-known ill-conditioned matrix. So to give you some idea of why this is a problem for our method, let's take a look at an example in MATLAB.